I'll be working through this guided note sheet on work energy, so I recommend you have this document handy to take notes on as we go. Part 1, what do forces do? Recall that forces are interactions. They represent interactions between objects, and a force has what we could think of as three jobs, three different effects. We've discussed already what a force does at an instant. The instantaneous effect of a force is encapsulated in Newton's second law. At one instant, a force causes acceleration. Force causes acceleration, mass resists acceleration. Newton's second law tells us how much acceleration results. So the instantaneous effect of a net force is to cause an object to accelerate. But when, however, a force acts over time, this was a force acting at an instant, but when a force acts over time, this sort of cumulative effect of a force over time, we've seen that results in a transfer of momentum. A force acting over time on an object transfers momentum. So interactions cause acceleration. Interactions also result in momentum transfer. And the impulse momentum theorem enables us to calculate that momentum transfer. So the net impulse on an object over some time interval, which is the integral of the net force acting on the object, the time integral of the net force acting on the object over that interval from time 1 to time 2, that results in the change in momentum of the object, momentum transferred to or from that object. So force acting over time transfers momentum, and our major interest at this point now is to look at what happens, look at the effect of a force acting over distance, the cumulative effect of a force acting over distance on an object as it moves along a path, as opposed to the effect over time. So this is the sort of accumulation of a force over time, results in a momentum transfer. Now we're going to look at the cumulative effect of a force acting over a distance, pushing on an object that's moving along a path. And we're ready to define the work done by a force. We're going to say that a force acting over a distance does work. And what we'll discover is that doing work means transferring energy. So force acting over a distance, we say it does work, meaning it transfers energy. So we've got momentum transfer when a force is acting over time, and energy transfer when a force is acting over distance. So the work done, capital W to represent work, the work done by a force acting over a distance will be the integral of that force dotted with an infinitesimal displacement. This dot is not just multiplication. This dot is a vector multiplication. We've got two vectors that we're multiplying together. It's called the dot product. We'll be discussing exactly what this operation means, how you multiply two vectors together, the dot product. And we'd be integrating along some path. This is a path integral. So the effect of the force acting on an object, pushing the object as the object moves along some path. And here, dr is some infinitesimal displacement vector, a tiny step forward along your path. An infinitesimal displacement, a little vector pointing in the direction that you're going. So on this graph here, this is sort of a map, really, an overhead view of the XY plane. And we've got an object moving in 2D along this curved path through that plane, starting at A and going here to point E. And at various points along the path, A, B, C, D, and E, I've indicated in blue a little displacement vector, an infinitesimally short vector tangent to the path at that point, pointing in the direction that the object is going at that instant. So a tiny displacement, a little step forward, always tangent to the path. I've shown force vectors on here as well, and we'll be discussing the relationship between those force vectors and those displacement vectors and how they relate to the work being done by that force and the energy being transferred by that force.